You can measure a right angle without measuring the angle. Mark 3 meters along one side of a corner and 4 meters along the other. Now pull a tape between those marks. If the distance is exactly 5 meters, the corner is square. A tape measure has revealed an angle. On a large site, even a small error here can shift a wall far from where it belongs. But why should squaring two lengths tell us anything about 90 degrees? Adding 3 and 4 gives 7. But 7 meters is the route around the corner, not the straight line between the endpoints. The diagonal is a different kind of journey. One displacement across two independent directions. The right angle is clearly doing something. What exactly does it contribute? To answer that, we need a relationship that combines horizontal and vertical movement without pretending that the bent route and the direct distance are the same thing. The compressed relationship is this: a squared plus b squared equals c squared. The letters A and B name the two legs, the sides that meet at 90 degrees. The letter C names the hypotenuse, the side opposite the right angle. Rotate the triangle and those rolls rotate with it. C is not whichever side happens to look diagonal. Its position defines it. But the first real mystery is smaller. Why are the lengths squared? Build a literal square on a side of length A. Its area is A times A, or A squared. The exponent does not mean twice A. It converts a length into an area. Build squares on B and C, and the theorem becomes a claim about 3 areas. The two smaller square areas exactly equal the larger one. The units provide an honesty check. Measured in meters, every term is in square meters. We are adding area to area, not length to area. Only after taking a square root do we return to a length. But a picture can suggest this equality without proving it. Why must those areas balance for every right triangle? Now comes the real test. Can we prove the equation without choosing any numbers? Take 4 identical right triangles. Each has legs A and B, hypotenuse C, and area 1/2 times A times B. Place them inside a larger square whose side is A plus B. A new shape appears in the center. Each of its 4 sides has length C. It looks like a square, but appearance is not proof. Are its 4 corners really right angles? The 2 acute angles of a right triangle add to 90 degrees. When neighboring triangles meet, those 2 angles meet as well. Together they make a right angle. So the central shape has 4 equal sides and 4 right angles. Now we may call it a square, with area c squared. The outer square can therefore be read in 2 layers. 4 identical triangles plus the square in the center. The outer area is A plus B all squared. The 4 triangles together occupy 2 times A times B. Every part is counted once. Nothing is estimated. Now move the 4 triangles. Do not resize them. Do not alter the outer square. Same square. Same 4 triangles. Same occupied area. Therefore, the uncovered area must also be the same. Before the rearrangement, that empty area was c squared. After it, the empty regions are a squared and b squared. The same whole minus the same 4 pieces leaves the same remainder. So a squared plus b squared equals c squared. This is not a numerical coincidence. It is a conservation of area argument. And that is the proof. Return to the measured corner. 3 squared is 9. 4 squared is 16. Together they make 25. The positive length, whose square is 25, is 5, so the diagonal must be 5 meters. The theorem also works in reverse. If 3 side lengths satisfy this relationship, the triangle must be right-angled. That is why the 3-4-5 pattern can test a corner rather than merely calculate a missing side. The numbers are not magic. They are one integer example of the relationship we have just proved. Builders and surveyors can scale that pattern to 6, 8, and 10, or to any convenient multiple. But the physical measurement is never as perfect as the geometry. Sloping ground, tape tension, instrument error, and working tolerances still matter. A cord can sag, a stake can move. The theorem is exact, the act of measuring is not. The same triangle hides inside every coordinate grid. The horizontal change is one leg. The vertical change is the other. Because the axes meet at 90 degrees, the direct distance between 2 points is the hypotenuse. Square the two changes, add them, and take the positive square root. A negative coordinate difference causes no difficulty because its square still records the size of the change. The Pythagorean theorem has become the distance formula, a rule for turning separate directions into one measurable separation. The compact formula still stands on conditions. The sides must be straight. The units must agree. The triangle must lie in a flat Euclidean plane, and A and B must meet at exactly 90 degrees. Now keep their lengths fixed at 3 and 4, but change the angle between them. Close the angle. Before the number appears, predict what happens to the opposite side. It becomes shorter. Open the angle beyond 90 degrees and it becomes longer. Nothing happened to the known lengths, only the angle changed. The formula remembers a condition that it does not display. For a general triangle, the missing information appears in the law of cosines. C squared equals A squared plus B squared minus 2 times A times B times the cosine of the included angle. That final term corrects for directions that are not perpendicular. At 60 degrees, sides 3 and 4 produce a third side of about 3.61, not 5. At 90 degrees, cosine is 0, so the correction term vanishes. The famous equation is therefore not a universal triangle rule. It is the exact right-angle case of a larger relationship. This relationship was studied in Babylonian, Indian, Chinese, and Greek mathematical traditions long before the modern equation existed. Its familiar name is not its complete history. No surviving contemporary evidence establishes that Pythagoras discovered it or supplied the first proof. Around 300 before the Common Era, Euclid recorded a geometric proof in the Elements before symbolic algebra gave the theorem its familiar form. The search for proofs did not end in antiquity. In 1876, an Ohio congressman published an original trapezoid-based proof. 5 years later, he became the 20th President of the United States. His name was James A. Garfield. He calculated one trapezoid's area in 2 ways. When the calculations were made equal, the theorem appeared again. Same theorem, another route. We began with a practical trick: 3 meters, 4 meters, 5 meters. Now we know why it works. The squares are areas. Their equality comes from geometry. And the right angle is the hidden condition holding the relationship together. The equation is not merely a recipe, it is a compressed argument with a boundary. A right angle turns 2 independent directions into one distance. For more great equations opened in this way, subscribe to QuestionKind and continue with the next one.